Hello, everybody. Thank you for attending this session today. My name is Shreyas Ramesh, and I'll walk you through what we are doing at Accenture from a quantum computing standpoint, and specifically quantum in telecommunications, telecom. I lead our quantum practice from a quantum computing practice globally at Accenture, which means that I do a lot of the cool work from implementing the technologies and integrating each and every single one of them for Accenture. So today, what are we going to talk about? We have a couple of really cool topics ahead of us. First and foremost, we want to make sure that we cover really what is our general perspective around quantum computing and where are we and how do I go about approaching a lot of these problems that from a quantum computing standpoint. Then we're going to touch really quickly around the impact of quantum computing in the telecommunications industry. And we know that the field is very large. Quantum and telecom is very large, and there are many areas that we'll focus. But for today, we're going to focus on a lot of the near-term applications. Following that, we're going to talk a little bit more of a deep dive from that section into more of the interesting problems, the more popular and the more interesting problems that we've covered in telecom for quantum computing. And finally, because quantum is a very broad topic, just quickly introduce some of the areas outside of the compute aspects of quantum computing more into the actual quantum aspects of it. So today is just a quick overview of our approach. And we know we've been leading the way from a quantum computing standpoint for quite some time. Since the mid-2010s, Accenture has been exploring quantum methods and applying techniques to practical real-world scenarios. We're on the cutting edge of quantum software development and implementation of today's NISQ era hardware. And so we do this because you've heard this throughout the D-Wave presentations. It's thanks to the ecosystem of partners and people and universities that were advancing the topic of quantum win. And this can't be possible without the people who are backing these efforts. So we've got hundreds of contributors across the globe helping advance the topic of quantum computing. And what we're doing is with our clients, we're taking a lot of the research that we've applied since at that point in time with a massive use case library, with a massive list of integration patents and a library of methods that we can use to advance these topics. To further some of these areas, also we've got 30 or so different fully functional cloud-based applications that are very industry focused, that run on a lot of our custom formulations that you can kind of click through and view the demos of these applications to show that there's an actual real impact in the area of quantum. And we can't really, we take a lot of these things forward with our clients with a series of ways to explore this topic of quantum computing. So our approach in exploring quantum is multifaceted, right? We want to shift the way in which an enterprise approaches quantum computing, and our vision is to be very business-centric, right? So we want to make sure that we have the appropriate funding from the top-down perspective. We want to make sure that the designated quantum leads within our clients are fully engaged, fully focused, and it's not just from the IT, but even from the business standpoint. We know that this can't really necessarily happen with just doing it because it's cool, so to speak. There's definitely a coolness factor to quantum, but we want to be very business-led to ensure that there's potential business value that is going to come from these real practical quantum computing applications. And doing a lot of these things, we want to make sure that quantum is definitely integrated into the enterprise's infrastructure, if at all possible. And we want to do this at scale to ensure that our clients can see the value of this, not just immediately from a POC standpoint, but potential value that may arise for when quantum computing is fully ready for prime time and production. So we talked about the approach very quickly, right? We know that the fundamentals of the way in which we work in a lot of these multifaceted, data-centric environments are definitely changing the way in which how the industry wants to focus on a specific problem. So what do? Right? We target specific enterprises with use cases across nearly every vertical. And Accenture has been doing this thing with our clients constantly. We're very business centric, so we understand that specific industries in the areas of communication and media is what we're going to talk about today. Would want to bring some very specific use cases to them. Use cases in this particular area, right? We said we mapped hundreds of different use cases. Specific use cases around, for telecom, at least the most popular ones are like network build and maintain and operate, the infrastructure, because it's a very difficult problem to target. The product and service recommendations, because telecom providers or any clients for that matter would want to apply very, very difficult situations, difficult problems to their scenarios that they have, to the use cases that they have. Fraud detection, inventory management, and supply chain optimizations are one of those key areas. And quantum computing, you can apply this thing on various different algorithms that are out there. And there are a lot of very major algorithms that can help progress this area of quantum and quantum research. Specifically today, given it's a very D-Wave focused call, we want to make sure that there's annealing-based problems that we want to focus on. But given the recent announcement from D-Wave, I think there's a whole plethora of different approaches that we can take a look at as well, given the gate model use that we just heard today. So with that being said, and knowing this is how we map a lot of these use cases and drive down to how the specific algorithms within those use cases are going to be made relevant, we want to really dive a little bit deeper into this particular field of telecommunications. We know it's very large and can cover various different areas in the field of quantum. But specifically, what we're going to target about today, we're going to focus on today, are some of these near-term applications. The various different application domains that we have, right? So quantum computing, we can categorize all the application domains into these domains that you're seeing up here, which is around quantum computing, which is optimization and machine learning, and you have communications and cryptography, you got control and sensing from a hardware standpoint, and the fourth one is really around preparation in the event that you want to making sure that your networks are secure, etc. And I'll deep dive a little bit into each and every single one of them. Now, for all of these, we know optimization problems are probably the most used, because most of the problems that the clients have are problems in our daily living that have elements of optimization in them. And typically speaking, there are potential benefits to applying quantum computing in these areas. Specifically around how do I improve customer satisfaction, because the problem that we're targeting is a very difficult problem, like providing customer service product recommendations, for instance, or how do I reduce MTTR, right, or the reduction of that basic resolution time, because the problem that you're tackling is a very difficult problem, are one of those potential benefits. In the areas when you shift to the hardware and the communications standpoint, we've got specific benefits around it, that it's definitely a new revenue model altogether, and given that quantum computing is advancing so quickly, that it's definitely going to allow for a more secure network. And I'll dabble into it just a little bit to know that this is what telcos are looking into presently. So each of these areas, you have very, very specific problems that we want to target, right? And in the case of optimization, these specific problems come in the form of constraint satisfaction problems, or knapsack, or an integer program, or some kind of a scheduling problem, or risk minimization problem, or a network flow problem, whatever it is. And we wind up applying a lot of different techniques to ensure that each and every single one of those different problems as categorized as an optimization, can be fulfilled. Specifically in the areas of quantum annealing, these things are very relevant to advancing quantum optimizations. Furthermore, from a machine learning standpoint, we're seeing telcos take a look at more of the prediction and estimation, data classification problems, or segmentation and recommendation-based problems as well. And these sorts of techniques that are typically applied over here are in the form of a feature map, a quantum Monte Carlo, probabilistic sampling, or a quantum variational autoencoder, to kind of figure out how do I address a specific pain point that they're going to have. And you're going to see some of those examples in the following slides, so you get an idea of what they are. I'd be remiss if I didn't mention those similar areas from communications and cryptography, where you got QKD, you've got quantum key distribution, quantum networking for fault-tolerant quantum computings, post-quantum cryptographic protocols such as BB84, E91, where are specific techniques that are applied over here. Or you talk about, telcos talk about quantum error correction codes for QKD or quantum key expansion protocols from a communications and a cryptographic standpoint. These are some things that are being talked about right now within the telcos, and people are experimenting with it. From a hardware standpoint, when you talk about control and sensing, we hear a lot about what are the coherent controls for qubit operations. D-Wave thinks about this constantly as well. The calibration of these physical devices itself, and you apply techniques to advance these topics, such as flux qubits, which is what D-Wave's been doing all along, and superconducting, quantum interference devices to help with a lot of that calibrations or ensuring you have coherent controls. These are some of the topics that telcos are also looking to advance as well. Now, I kept the fourth section over here more along the lines of you don't need a quantum computer to help prepare you for these communications, cryptography, and control and sensing. We want to make sure you adapt the networks to be crypto agile. You perform a crypto agility assessment on it, and there are tools to advance that component. You talk about simulating quantum networks, where you got quantum network security or quantum computer interconnects and quantum sensor deployments themselves. And interestingly enough, there are tools that are out there to help simulate a lot of the deployments of these quantum interlinks across these various different networks. And so these are some of those techniques that are applied in those specific areas from a hardware standpoint. So let's get to some of those really interesting problems that I basically alluded to. And you've heard these problems in the past, and now what you're going to hear is there are clients who are actually clients of ours who are actually interested and are exploring these topics further. In the case of, we're calling this thing a joint optimization of network design and construction. This is more about building a network or constructing this network, right? The network design is a complex optimization problem. The joint optimization as at backbone and access levels to optimize both the topology and the locations is a very hard thing to do. Consider quality of service and projected traffic and SLAs and various delays that gets occurred as a part of your network. Consider the cost, the construction of the cost, the energy of the network that it's going to take, and the frequency allocation of it, spectrum sharing, etc. These are real challenges. And so network construction scheduling needs to be optimized. Scheduling the construction of these network segments, whether it's for example, a fiber rollout that's out there, to maximize the return of investment over time, continuous rescheduling based on progress and demand, and continuous modifications and expansions are real issues, real things that they need to start thinking about. And so what do we wind up doing? We model this network construction scheduling as a mathematical optimization problem. And quantum computing in this scenario, we know is a promise to provide a more scalable, more efficient solution compared to the traditional methods for any combinatorial optimization problems. So the optimization problem modeled as a multi-site hub with the shortest path problem, or we're taken into consideration in this particular scenario, where you want to make sure you prioritize the site to hub communications. And if you know anything about network layouts, that winds up becoming a very complex network. And so the joint and continuous optimization of network design and rollout schedules provides the opportunity to improve any kind of efficiencies for this one particular telecommunications company. And so they are, so we're doing this with, going back to being very business centric. We want to provide these very key benefits to the clients. And so these are some of the potential benefits, value drivers that the clients wanted to target while working on this particular type of a use case. And we're tracking towards it from a strategic perspective, from a top-down standpoint as well, to making sure that this particular use case does see value. Another one is making sure you have an integrated, so if you have like a 5G operations center, right, you've got the multidimensionality and the dynamicity of heterogeneous devices that are out there, to making sure that we can track on where some of these errors could happen. The sheer volume and the size of the different things that you have to monitor is vast. It's like you can see over here. It's by 2025 you're going to have about close to about 40 billion different devices generating close to 80 zettabytes of data. Right? That's a monumental amount of data. So what we wanted to do is we created a POC with this from a telecommunications standpoint, the solution to perform very practical hybrid and heterogeneous networks of these billions of devices hooked in together and the data points associated to it. And what we wound up doing is we wound up creating a minimal set cover technique to kind of efficiently perform a root cause analysis for these different devices and where those errors happen. So the operations center can quickly focus on what's really important to them. The next one, we mentioned from optimizing any kind of customer experience, right? In today's world, not just telecommunications, various different worlds, you have various different mergers and acquisitions happening all the time. New customers are coming in, new services are coming in, and we know that typically speaking with these customer service providers that with the growth that exists, with the customer loyalty that you want to track to, it's just really hard to do that with a traditional rule-based engine. And to optimize these various sequences of omni-channel situations where you're recommending products and services for a specific customer in near real-time or real-time decision making, to optimize on that, the simple optimization aspects of that is a very difficult problem. And so what we wound up doing is we wound up creating a solution that leverages a hybrid solution, that leverages D-Wave's hybrid to explore how to make these service contents are the best within to be presented for a customer. And the recommendations presented and was provided with multiple different constraints associated to it to ensure that whatever that's happening is not only what's best for the customer, but it's also best for the company that's providing these recommendations as well. And again, like I said before, we wanted to make sure that we deliver business value to the customer, and so there are potential key benefits associated to doing this as well. The last very interesting use case that came about is, supply chain optimization. So we know supply chain planning involves multiple decisions for sourcing, production, storage, and distribution of products. Intelligent decisions are needed to achieve operational excellence. And there are trade-offs between revenue costs, service levels, etc. For example, a customer asks for higher quality, lower price, faster delivery, and guaranteed availability of it. And the volatility of any kind of operational and transportational costs require constant monitoring to ensure financial stability of the operations. And a combination of these various different hundreds of different products and constraints and transports, etc., it's just going to become a very complex problem to optimize on. And just to give you a brief idea, right? So some of those variables that you want to take a look at, right? The amount of goods that are in here, what's being produced, what's being stored, what's being purchased and sold, etc. And these constraints all meet these demands, whether it's a minimum or a maximum, just makes it simply a very, very hard problem. And so we worked on a couple of these use cases, tapping both QIO, 1QBit, and D-Wave hybrid, and also classical MIPS solvers to actually yield some of these potential benefits that is relevant for our client over here. Now, as I said, I would be remiss if I don't mention the other areas of where telcos find quantum as a very interesting topic. First and foremost, our telcos are exploring quantum computing as a service, where they want to try to take a look at, okay, how do I implement quantum simulators in my ecosystem, and how do I then ensure that you have quantum-inspired classical solutions through the network that they provide. And they also want to do this while optimizing their pre-existing infrastructure as well, right? So a telco basically provides infrastructure to their clients from a B2B standpoint. And a lot of this infrastructure they provide requires to be optimized to serve the client's best interest, or their client's best interest, so to speak. And so optimizing on that by its own self is an NP-hard problem. So they're trying to tackle that as well. Now, in the area of quantum cryptography and communications are important uses of quantum resources, in which information could be encoded in quantum states and sent to another party via quantum channels, with the ability to perform better eavesdropping detection and more secure information transmission. This is existent for the clients, and it's important for them as well. Finally, now I wanted to quickly touch on multi-party communications could be enhanced by quantum teleportation-based techniques such as entanglement swapping, or other components such as quantum repeaters are also key to the realization of QKD protocols, and their achievements and their advancements are what I've been closely tracking towards. Now, these are just to kind of give you guys a glimpse very quickly on what's really important for our telecommunications industry and what they're trying to focus on. With that, I would like to thank you all very much for listening to me over here. And as always, if you have any questions, please post it in the chat. Myself or my team will get back to you at the very earliest. And we're very eager to explore quantum computing with you all. Thank you so very much.